AP Calculus, BC, Lesson 5.2, Mean Value Theorem. So this is going to look a little familiar, the mean value theorem for derivatives. It looks a lot like a derivative. We got some key pieces to this. If the function is continuous on the closed interval and differential at every point on the open interval in its interior, then there is at least one point that matches up the derivative. So that says here's a function from here to here. There is some point in here that is parallel to the derivative. So how's that different? Well, we don't actually have to do anything. We can use our old derivative techniques to do our thing. It just means that the derivative has a parallel line. And then the big question is, well, why would we bother doing that? If, by the way, just watch out for those prerequisites. Let's open some doors to something called increasing and decreasing functions, which are very obvious, but yeah, math, that's the answer. So we call this an existence theorem. We do not learn how to calculate things. That there's a parallel chord exists if the hypothesis is followed. So first things first, is it continuous? F equals x squared, f of x equals x squared. It is continuous and it is differentiable from 0 to 2. Continuous would be that, and differentiable would be that. So I'm not going to get into that right now, but definitely watch out for it. So find a solution. So the derivative is 2x, and then we're looking at f of 2 minus f of 0 over 2 minus 0. So we get 2x equals 2 over 2. And we're saying there's some solution c, so we plug that in. 2c equals, oh my bad, f of 2 is 4 minus 0 over 2. And we'll say 2c equals 2, therefore c equals 1. So if we draw a graph, and this is 0, and this is 2, we can say that that line and that line, those two lines are parallel. That's what the mean value theorem means. So try again, except these are going to fail. Interval -1 to 1. It works. You can put -1 to 1 in. Nothing wrong with that. And then is it differentiable? And the answer is yes, except for a certain spot. Square root of x squared just basically means absolute value of x plus 1. When we graph that, you get this. And it doesn't go on forever because it's from -1 to 1. So continuous. Yep. Differentiable. Nope. So, is there a line parallel to this? No, there's not. Because at 0 it just doesn't work. So, by the way, this says that there will definitely be an existence if you fulfill all the hypotheses, but it does not say it won't happen if you don't. It just says it's not guaranteed. So this one, whenever I see piecewise, I graph it because we don't need a calculator to do so. Less than 1, x to the third plus 3. 1, 2, 3. At 1, that would be 4. Open dot. And at 0 would be 3. And I know it does this sort of thing. And then at 1, we get 2. This dot's filled in, and it's x squared plus 1, so it's going like that. So we would say continuous, and we would say no. And we got a little problem here. These are on -1 to 1, so gotta fix all that. So it just jumps from here to here. Doesn't work. So another example. F of x equals square root of 1 minus x squared. A equals -1 to whatever you get when you put in -1. Let's play with that immediately. -1, I put that in, I get 0. B equals 1, I get 0. Find a tangent f in the interval -1 to 1 that is parallel to the secant AB. Is this a mean value theorem? No, not closed. But like I just said a few seconds ago, okay, that doesn't mean we can't find one. It just means that we aren't guaranteed to have one in there. We could argue it's continuous from -1 to 1, but I mean, the way the question is asked, it's definitely not good. So let's check it out. Derivative is 1 over, excuse me, it will be 1 over square root of 1 minus x squared times -2x. And if I put in this point, I get 0 minus 0, unless I'm very mistaken, over second one, 1 minus -1. Not that it matters because we get 0, so x has to equal 0. That's where the graph has a horizontal tangent. That would be equivalent, because if you drew a picture of this, I believe you would get something like this. Yeah, this would be a 1. So somebody says, what's the derivative that goes through these points? I'd say, pardon me, what's the slope of the line that goes through those points? I'd say it's equivalent right there. So this gets used a lot in these goofy questions, excuse me, about my accelerated car from 0 to 60, ended up going 20 miles an hour, then I slow back down. That means that if I went from 0 to 60 and back down, at some point, up to 20 miles an hour, which is ludicrous, but at some point I was going 10 miles an hour on the way up, and I was going 10 miles an hour on the way down. So it's just an existence theorem. It means those points have to have been hit at some point in time. So here's increasing and decreasing. It's related to the mean value theorem. I won't go into how much it is and why, because quite honestly, I don't know. But it says if a derivative is positive, we're increasing. If it's negative, we're decreasing. If you look at a graph, you'll know what's going on. We'll do that in a second. You notice it's increasing on a closed interval, and this causes worlds of problems. I can try to explain it, but I'm not very good at it. And regardless, let's look at y equals x squared. On this side, it's decreasing. On this side, it's increasing. And like we just said, f prime of x is greater than 0. And that would be on the interval 0 to infinity. Notice infinity is not closed because you can never actually get there. Over here, f prime of x is less than 0, and that's on the interval -infinity to 0. Let's try another one. What about the function f of x? Check the derivative. 3x squared minus 4. So we want to know where it's increasing. When is it greater than 0? Well, we solve it, we get 3x squared has to be greater than 4, x squared has to be greater than 4/3, x has to be greater than 2 root 3 over 3, plus or minus. So you gotta throw down a number line, and you gotta check out the derivative. So you put in 0 to the derivative, and you get a negative number. You put in something greater than 2 root 3 over 3, which is, we'll call it 10, just to keep our life simple. 3 times 100 is positive. Same thing with the negative, positive. So we are increasing negative infinity to 2 root 3 over 3 inclusive, and negative 2 root 3 over 3. We're increasing from 2 root 3 over 3 to infinity. We are decreasing from negative 2 root 3 over 3 to 2 root 3 over 3. The reason these are closed intervals is the definition says let's compare two spots. And I can't compare the spot that's infinitesimally close to the end of the interval unless I have the end of the interval to compare it to. Does that make sense? Great, congratulations, because I'm not sure it makes sense to me. Increasing, yeah, I just want to make sure I got my question right. Yeah, good. Here's a fun one. If a derivative is 0, then the function was a constant, meaning f of x equals anything, 12. We just call it c. When I take the derivative, I get 0, which I say, well, duh. And then if we say two derivatives are equal to each other, then there's a constant that separates them. Constant could be 0. So when I take the derivative left, I get f prime of x. I take the derivative right, I get g prime of x. And I take the derivative of a constant, it vanishes. Well, this feels like they're giving us just the smallest taste of anti-derivatives, anti-differentiation, and integral, the process of finding integrals. But we'll see. So here's one. Find a function whose derivative is sine of x and whose graph passes through point 0,2. If the derivative is sine of x, then the function is negative cosine of x plus some constant. I think, gotta check. F prime of x equals derivative of cosine is negative sine, negative negative is sine. Derivative of c vanishes, looks good. It passes through the point 0, 2. So this was just to check. This I put in 0. I get out 2 negative cosine of 0 plus c. Cosine of 0 is 1. This is negative 1. So 2 equals negative 1 plus c. C equals 3. The function is f of x equals negative cosine of x plus 3. Boy, I sure hope I got that right. So very much going on. Hey, I got it right. Cool. When we write the function, somebody says, here's the derivative, it's f of x. We will typically write the original function as f prime of x. So I say f of x equals dot dot dot. What's the antiderivative? We would say f of x equals dot dot dot. That's called the antiderivative. We will get into this much more in the very near future. So back to velocity and position functions. Using the antiderivative. Well, if acceleration is, I got to put a negative in here even though it's not being shown, 9.8 meters per second squared, but I'm going to chuck units out, just keep them out of the way. Then the velocity is negative 9.8 t plus c, because if I take the derivative of that, I get the proper acceleration. Now, it starts at rest, so that's the velocity, because c equals 0. And it doesn't say where the body starts by the velocity position, so I'm going to have to assume it starts from 0, 2, because it would be negative 4.9 t squared. Don't believe me? Check it out, plus some constant c, which we really don't know. They did not say where it starts. Oh wait, it starts from a height of 0. So displacement is negative 4.9 t squared, because the height is 0. If the acceleration is 9.8, acceleration is, and again, negative 9.8. Then the velocity is, okay, we just did this, negative 9.8 t plus some c. Oh, the body has an initial velocity downward of negative 1. So negative 1 equals negative 9.8 times 0, because that's the initial time, plus c. We get c equals negative 1. The original velocity equals negative 9.8 t minus 1. Still starts at a height of 0. So the position, I don't know why I'm writing d, it should be s of t. Fix that, quite annoying. Is negative 4.9 t squared minus t plus some constant. Well, starts at 0 at time 0, so boom, boom, the c is 0. And here's our new displacement. You can plug numbers in and see what's going on from there if they asked. That's all we got for now. That's a lot of stuff. So, get going on some homework problems and try and make sense of it. Happy mathing.